Welcome to the defense of Abdoulaye Diop. So I'm Marc Baboulin. I'm a professor at University Paris-Saclay, and I would be chairing this committee. And so please, Abdoulaye, so you can start your defense, and you have 45 minutes, and then we'll have questions afterward.
Hello everyone. So thank you for being here for my PhD defense. Thanks for the member of the jury to be available for this date in particular. So I'm here to present my thesis, which is about insider threat detection system in the context of identity access management. So it is a thesis in the context, an academic context that I did in the CIPAD laboratory and also in an industrial context in the Ok. Je vais essayer de parler plus fort du coup. It's a thesis I actually did in the, like I said, in an academic context with IPAD and the laboratories, but also in industrial context with the Atos and Nvidia company. So my supervisor was Professor Nate Ahmad and Mr. Chai Winter. So I will give you a little bit of context about my work. So it's about, like I said, insider threat issue, which is one of the hot topic in the cybersecurity domain. And I will talk about the solution that cyber experts propose today, which is around the topic of user and entity behavior analysis. But mostly, I will describe the solution I propose, which is a scalable machine learning behavior classification method. So for a little bit of context, identity access management systems are tools that allow to control the manage access right to organization assets to different employee or user of IT systems. So these type of systems do this by controlling process such as identification, authentication, authorization. But even though they are efficient tools, they are still serving against insider threat. So to define insider threat, we can say that insiders are individuals with legitimate access right, but they use this access right to do malicious actions with information assets. So the objectives are mostly about data theft, sabotage, or industrial espionage. And we have actually essentially three types of insiders. So inadvertent actors, traitors, and masqueraders, who are actually black hat hackers that steal means of authentication to normal employees and impersonate as them in the organization. So the solution for insider threat is actually using entity behavior analysis. It is a three-step process that is based on user activity monitoring, which is actually the collection of employee and IoT object event activity data. And with this data, we do behavior analysis, meaning that we model normal behavior, and with this, the created model, we detect abnormal behavior. So with this created model, we can actually build a lecture system or contextual decision systems. So today, insider threat detection tools have issues. When they are based on expedited rules, they cannot detect novel types of attacks. And when they are based on machine learning solutions, they struggled with machine learning problems such as high false positive and false negative rates, and overfitting and underfitting issues. And this has the consequence to that these systems have present a lot of alarms, false alarms, and a lot of non-detection. So if you focus on machine learning approaches, they have these challenges, from data availability to the evolution of behavior. And in order to meet this challenge, in my work, actually, I proposed a solution which is based on the combination of ensemble learning, machine learning techniques, and a unite and conquer approach to deal with the different challenges. So my presentation will follow this plan. I will first of all talk about the theoretical basis of my contribution, deep dive in my contribution, which is, like I said, essentially a unite and conquer framework for ensemble learning, and also talk about a methodological analysis of this framework, and finish by present you the performance analysis of the implementation of the framework. So, for the theoretical basis of the contribution, this part will follow this plan. Actually, I will introduce to you the machine learning detection techniques that exist today. After that, I will present the ensemble learning methods to mitigate some machine learning issues, talk about the unite and conquer approach, and finish by describing the datasets I use for this work. So, I focus about the machine learning techniques used to detect insiders in organizations. We have supervised classification methods when data with label is available. Unsupervised methods, since we can consider an insider as an anomalous behavior, so it's an anomaly. We have multiple ways to do anomaly detection for this problem. We also have approach based on graph-based methods. So this is kind of a different approach to tackle the problem by looking at anomalous node representation of the data in the graph or anomalous links, and also clustering techniques for a visual analysis of clusters of behavior in organizations. So what's the ensemble learning interest for this case? So like I said, we have a lot of underfitting and overfitting issues with the solutions that are based on machine learning. So ensemble learning methods are methods that are known to deal with this type of solution. So you can give the example of bagging, which allow to reduce the chance of overfitting, and boosting, which allow to reduce the chance of underfitting. And also, we can also reference the combination of these two types of methods that allow to mitigate the bias variance trade-off. We focus about unite and conquer. So, unite and conquer, it's a method that allows to accelerate the convergence of iterative methods by making them collaborate. And this collaboration is did at the end of a cycle of iterative methods. Here it's called co-method. And at each end of the cycle, they are sharing interesting information between them, like you can see here. And this information is used to restart a next cycle with better initial conditions. Essentially, the most important part of this approach is a function f that allows to modify the solutions and improve the initial restarting conditions. So this is based on the work of Professor Naïd and Professor Serge. So here you can see one algorithm for unite and conquer. So it's based on the computation of the solutions, different solutions with different iterative for different generative methods with different initial conditions. And the most important part, or the two most important parts, actually the share of informations with all of process and the restarting function here to update the starting conditions of the different methods and also to improve them in order to accelerate the convergence. If I focus on the datasets I use in my works, so it was essentially an open source synthetic dataset from the University of Carnegie Mellon. So it's a 1-year timestamp dataset with different activity files, the logon, email, device, and activity of different employees. And in this activity file, they have 5 insider threat scenarios, but I mostly focus in my work on these three scenarios: data theft, industrial espionage, and high privileged access abuse. So, if I focus about the contribution, I will essentially talk about an overall insider detection systems that I developed, the pre-processing strategies, because it's a machine learning system, the UCEL framework behavior profiler. So with the framework, we actually create a module called a behavior profiler, and the core methods of this behavior profiler, and also different parallel programming models to build a scalable solution for this. So for this work, I actually proposed an architecture, a component-based architecture, mostly a container-based architecture, which follows a machine learning pipeline. So each part of the pipeline is on its own container. So I have a container that manages the data lake, a container that manages the exploratory data analysis. So it's important to analyze the data to actually establish new pre-processing strategies. And a container with the pre-processing and the training and validation part of the pipeline. So it's here that we implement the UCEL framework, so the methodological contribution of my work. And the trained models are actually saved in a file system and are used after to create an anomaly scorer that have actually the role to classify label data or unseen data to detect if they are normal or abnormal before sending them back to the streaming bus, and send this anomaly score to other cybersecurity tools to allow them to take decisions or create an alarm system or create alarms based on the result of the anomaly. So for the pre-processing strategies, their role was to actually have a lot of angle to attack the problem of insider threat. So in this work, I actually build user profiles, so subset of data made of user past activity actions. Role profiles, so it's a collection of users that actually have the same job. Natural language processing, so it is about getting suspicious word use or string use during attacks and create new features to detect the anomalies. And activity frequency, that compute the activity of different user or employees in the organization, meaning the activity in an hour or a day or a week timestamp, set of timestamp to detect if there is something strange in the activity. And with these processing strategies, the goal is to build the UCEL framework behavior profiler. So the role of the behavior profiler is to actually be trained and to detect if new activities is normal or abnormal. And it is created by actually combining, like I said, ensemble learning techniques and the unite and conquer approach. And overall, it's a semi-supervised iterative process that use oversampling the oversampling of wrongly classified elements proposed by Haidar et al. And it's actually, there's actually a representation of this process with when we start with raw active user activity data that pass to a preprocessing unit, and this data is actually split into training data and validation data, but also it's a validation data that is augmented by human feedback. So human operator adds some samples that he knows that are normal or abnormal activities, and since it's combined ensemble learning techniques such as bagging, so we create the bags, and these bags are actually trained individually, and a precision test is made, and following the principle of unit conquer, a synchronization and threshold testing phase here is done, and if the threshold that I fixed at the beginning or number of iterations is not reached, an ensemble of wrongly classified elements, so fake false positive and false negative chunks, are re-injected in an oversampling unit, like it is proposed in the work of Haidar et al., to augment the data that are misclassified and injected to the training data. So it's the feedback loop, a feedback loop that we can see in the boosting process. But the oversampling unit idea was actually an idea for Haidar et al. That I combined with the Unite and Conquer idea to actually augment, like I said, the training data for the next cycle, and then having a training data that allows to have a better decision boundary. So this process is actually repeated until either the convergence is reached or the number of iterations is reached, and this allows to create a most efficient classifier or an ensemble of classifier that is used as a behavior profiler. So to detect normal or abnormal. So here is an algorithm of this UCEL approach. So it's following the same basis at the Unite and Conquer algorithm. However, the function, the restarting function here, is the oversampling function that I choose to actually augment the wrongly classified elements, so the false positive and the false negative elements. And at the place of iterative methods, we have learners, so it's machine learning methods, that at each cycle, like I explained in the schema, give the result of testing and the wrongly classified elements. So the schema and these algorithms are, and the overall approach UCEL, were validated and published in these articles. Let's focus about the core methods that we can use in UCEL. So here we have, for a graph-based method, a graph-based method that is based on the use of PageRank algorithms to detect anomalies. So it's a work from Yao et al. That use graph-based, so exactly to be more exact, PageRank as an indicator of anomalies. So in this schema, I represented actually in yellow and blue the approach proposed in the Yao et al. Article, and in green the added informations, the added part I did in my work actually. So Yao et al. Proposed to use distance-based graph, so an Euclidean, an epsilon graph, to actually compute the page rank, the personal page rank of the node of the graph to determine if the node of the graph are normal or abnormal. So the page rank is an indicator of anomaly existence. And in the article, they give hints of the use of KNN graph. So it's exactly what I did in my thesis. So I use the KNN graph capabilities to do hyperparameter tunings, so hyperparameter tuning at the level of the number of neighbors and the damping factor for the PageRank. And I added these different blocks in green to actually build an anomaly detection method for inside a thread. So there is also another method that is this time based on autoencoder and LSTM combination. So the use of an LSTM type neural network was proposed by Renal, and I decided to combine it with an autoencoder LSTM method. And why an autoencoder in this case to do anomaly detection is that autoencoders are actually methods that allow to compress and decompress data. So we can use the reconstruction error of an autoencoder to determine if we have new anomalies. In this figure, you can see from January 2010 to March 2011. Now, it's actually a scenario of normal activity and an attack that occurred at the beginning of the 2011 year. And by plotting the reconstruction error of autoencoder LSTM here, we can actually choose a threshold of normal reconstruction error. And when an attack occurs, the anomalous reconstruction error, so since the data is different, the anomalous reconstruction error is higher than the normal reconstruction error. So the threshold chose is in the normal period here, allow to detect abnormal reconstruction error at the period of attack. So this is the second custom method. So these core methods can actually be implemented in the UCEL overall architecture. And if we think about the scalability of this model, so what I proposed is two types of models. Synchronous models that synchronous model when the core methods are affected to available node in a cluster, and when also we have a control node in separated node, and where all the computation of training and testing of the core methods are sent to a control node, and those control nodes do the oversampling step, and also the weighted multiplier step to actually send back the aggregation or all the different node works to them for the next cycle. So this is actually a synchronous parallelization approach of the UCEL framework I proposed, and it allowed to have better execution time, but better training time, but it used a lot of communication. There is a lot of communication since every time each method finishes test, you need to send the data to a control node, and the control node send it back to them after some transformations. So to avoid this number of communication, I actually proposed an asynchronous method. So here we have the same starting setting where we have the core methods are affected to available node, but they only receive information from other core method when these informations has been finished to be treated. For example, we have here two core methods, and each time they finish their testing set and we have new false positive and false verification, they send it to the other core method. So this approach allows to avoid the synchronization part and to have a control node, and this allows to, like I said, to diminish the number of communication and to have a better execution time. I will show more details in the performance analysis in the for the comparison of these two approaches. So, in the third part of my presentation, I will actually talk about, do a methodological analysis of UCEL. So first, I will analyze UCEL and the different techniques used to create it. And I will talk about one important part of UCEL, which is the oversampling techniques, oversampling unit. And for example, now if I start with UCEL analysis, so like I said, it's a semi-supervised meta-classifier ensemble that combine unite and conquer and bagging and boosting techniques. And bagging and boosting techniques allow to mitigate actually the high bias, high variance trade-off problem. And the unite and conquer to have a faster convergence. So this is a multiple trainings cycle process, so it's mainly for iterative models. But with the feedback loop, we actually inject in the oversampling unit, so only classifier element to actually improve the decision boundaries of the methods, local methods used inside the framework. And we can have a variation at the level of the oversampling technique we use. So if you do a quick comparison between oversampling techniques that we can use in this framework, we have here the synthetic minority oversampling technique and the random oversampling technique. And we can see that when we use the synthetic minority oversampling technique, we have the training size that is increasing in a higher level than the random oversampling technique. However, his high area under the curve is better, but it takes more time. So there is the trade-off to be considered here. If we choose the random oversampling technique or synthetic minority oversampling technique. Synthetic minority oversampling techniques allow to create new samples in the data. So it's allowing to add new informations to the training data, and then you have a better AUC score. But random oversampling, we use the same informations, but so we have actually less better score, but it takes less time. So there is a trade-off here, and we have to choose actually the one for the UCEL framework. So if I summarize the contribution of Noah, as a methodological contribution, we have I have presented a new meta classifier, an iterative combination of boosting and bagging, and a method with a great potential for parallelism. And for the software contributions, I actually presented a custom scalable implementations and overall insider detection systems that can be used to detect abnormal behavior. So in the performance analysis part, I will show the performance of UCEL behavior profiler. And I will do a quick comparison of UCEL versus boosting. And then I will show training and testing results. And finish by the parallel implementation test and an alarm system test. So if we look at the training of the training IC score of an execution of UCEL with here 6 co-methods, we can see that most of the co-methods are improved in the training IUC during the iterations. However, not all of them. For example, if we focus on iForest here, is not improved at all. And this is due to the fact that even if UCEL has the role to improve the training IC score, if the initial hyperparameters are poorly chosen, the process of improvement actually is not working. However, the all the method of UCELs are not blocked by a method who is not actually working. And we can see that overall, we have this this approach allowing to improve all the training AUC scores. Most of the training AUC scores. If you compare here UCEL with boosting, we can see that UCEL actually outperform boosting. If we consider the boosting of four classic anomaly detections methods, such as one-class SVM and local outlier factor. So this is pretty normal since UCEL actually use the principle of bagging and boosting in this process to combine them and to get better results. So it's kind of using the best from those worlds to outperform the classic boosting method. So for the comparison of training and testing results, so here we have 10 obscurance method for anomaly detection and 10 multiple layer perceptron and 5 supervised methods. And we can see here the training and testing accuracy with or without the use of this frame. So for the testing accuracies, we can see that with UCEL we mostly outperform all the method, all the testing accuracy of the method when they are not using it. For example, here for 4 anomaly detection, we have 0.52 as an AUC and 0.93 as an AUC with UCEL. However, when you go to the supervised method, we can see an improvement, but it's very small since at the start, the supervised method, the AUC is very strong, and even though the improvement is just 0.1, so we can conclude here that for methods that have a starting AUC, starting very strong AUC, we have an improvement, but it's very small. And we can conclude that since here we have supervised methods and here it's more about anomaly detection methods, and so this approach is more efficient for anomaly detection methods, and even though we have the improvement for smaller methods, it's kind of less efficient. So if we apply UCEL to the 3 scenarios I presented at the early 2 scenarios of insider threat attack, so data theft, industrial espionage, and privilege access abuse, we see that UCEL showcase pretty much good result, at the exception of privilege access abuse for 4 anomaly detection methods here, which is just 0.64. So here we can conclude also that we have an interest for insider threat problem to combine anomaly detection approach, but also supervised approach, since for some case, even we try to improve the training accuracy and the precision of the method, we still have some case that it doesn't work when it doesn't work very correctly. So all the results of the variation of the training accuracies and this different table were also validated and published in the IPCC conference. So now that I show you UCEL for the main problem of my thesis, which is insider detection, this is an example of UCEL used for another problem, which is breast cancer diagnostic, and we can see the same type of behavior when the training AUC score is starting very low. We can see that UCEL improved it, but for training AUC score here, which are starting very high, we have an improvement, but is less important. So it's kind of the same conclusions that we saw with the study. Here it's for another example of well-known TITANIC classification dataset. When we see actually the same behavior, so slow starting AUC scores are important. But we also apply this framework to more general classification problems, so multiple level classification problem and binary classification problem. And overall, it's the same. It's actually the same behavior that we observe. So let's focus about the parallel test, the parallel implementation test. Like I presented before, I have two parallel models to accelerate, to actually optimize the performance of UCEL. So a synchronous approach and asynchronous approach. So here in red, we can see the synchronous approach that has some performance issues when we are past 50,000 entries. And here, this is due to inside give a representation model of the synchronizations and the number of communications. And also to the fact that when we do UCEL, when we use UCEL in different co-methods, they actually have different execution for the training cycle. So what happened here is that when the model that takes more time doesn't finish actually his training cycle, every other model with the synchronous approach are waiting for him to actually go through the next cycle. And this situation is avoided when we use the asynchronous approach, since the models continue the training cycle with their own false positive and false negative, and only change drastically the training data when they receive new wrongly classified elements. So we can clearly see that the asynchronous model outperforms the synchronous model. So here are also some scalability tests. We do it for the framework. So for this example, it was 10 multilayer perceptron method, 10 multilayer perceptron co-methods with different hyperparameter to start. So it's multiple UCEL. And we can see that this model is scalable, and we have a speedup that is stable around 4.5, 4.8. And I also wanted to precise that all the parallel tests I did was done on the grid-ensemble test bed. So it's an ensemble of clusters situated in the cities in France. So the result of the synchronous approach and the scalability test were also published in the IPCC conference in 2020. I think it was 2000. And if we focus about the GPU impact, since one of the methods I presented, one of the co-methods was based on TensorFlow, and it was actually the method that was taking more time if we compare to other co-methods. I decided to see the impact of the parallelization of these methods by using the TensorFlow distribution capabilities. So using TensorFlow to distribute the training cycle of this co-method in particular, I can see here that the use of 4 GPUs allow to have the best speed up I have in my work. Actually, it was 10. So actually, it was not 4 GPUs, but it was at the level of 2 GPUs that I have the max speed up of 10 here. But we can argue that the size of the data I used for this example was, for example, 10 million samples, was limited factor for the GPU. But this is actually a proof that when we parallelize, so this co-method in particular, we obtain a gain that is not that is very interesting, and that also actually it results that we submitted to the to the CC Gate conference in 2022. So we are still waiting for the good news for this. And if I go to the presentation of the alarm systems that I talked about at the beginning, here we can see a scenario of normal activity and abnormal activity between 2010 August 8 and 2010 26th of August. So here in this schema, in this figure, we actually compare one alarm system which is based on the combination of lot of methods, the collaboration of the methods that you can see here in yellow, so advanced weighted score, and an alarm system which is only based on the best method score, so just one method machine learning. And we can see here that in the period of attack, so between 11 and 20 August 2010, we actually see that the anomaly score that proposed by the advanced weighted score are lower than the anomaly score proposed by the best method score. However, when the activity gets normal, one machine learning method, so the best method score, still give high number of alarms. So this means that this validates the fact that using an approach with the collaboration of a lot of machine learning methods allow to have more accurate result when we have an insider attack, and also this allow to answer the question of high false alarm and non-detection rate that I leveraged at the beginning of this presentation. So I can add that here we have two thresholds, and a context solution threshold and alarm threshold, and this this risk score, or anomaly score, if you prefer, can allow to take contextual decisions, so like authentication, assigning authentication level, so high factor of authentication level if the anomaly score is low, and a low factor of authentication level if the anomaly score is low, and a high factor for authentication when the anomaly score is high. So to finish my presentation, I will do a quick recap of what I presented. So this work was done to mitigate the insider threat detection issues. So when the solution is based on exploited rules, so they cannot actually detect new types of attacks. When the solution is based on machine learning methods, so they suffer from problems such as overfitting and underfitting and high false alarm rate. And as a solution to this challenge, I propose a scalable machine learning behavior classification method, which is based on the container approach for the global insider detection method, and the creation of a new meta classifier that is that use unite and conquer approach and ensemble learning, and that have a great potential for parallelism, like the two models I showed. And as a perspective of this work, we can actually talk about the use of this approach in a more general context, since I show example in breast cancer and also the TITANIC datasets, but I have a lot of examples for the classification problem. So it will be interesting to use more methods and see its impact methods on the precision of the global system and also the parallelization model proposed. We also can explore more oversampling strategies because it's one of the important parts of this approach, since it's the way to, it's the core, so it's like the F function of the Unite and Conquer approach. It's the main method, the main way to improve the result of the methods at the next iteration, and to also explore other distribution strategies to use this approach, the container-based approach, on cloud type of architecture. And ideally, I would like to publish all the general aspects of this work in the machine learning journal. So thank you for your attention. It was everything I had for my presentation today. And if you have any questions.
Okay.